The dot product is a way to multiply two vectors. And whenever you do a dot product, the result is always a scalar. So that means it's always just a single number. How you calculate the dot product is you individually multiply the entries of the two vectors according to which entry it is. And so if I want to take this dot product of u and v, I would multiply 1 times negative 1 plus 2 times 3 and so the dot product is 5. Let's do another one. This one, multiplying the entries pairwise and adding them together, looks like this. Negative 4 plus 0 plus 12 is 8. So does everybody understand how the dot product works? Okay. This is the only time I'm going to show you. So make sure you understand before we move on. Please raise your hand, ask questions if any of this isn't clear. And you can do a dot product with vectors of any size, as long as they're the same size, okay? Like I can multiply dot product these two 4-dimensional vectors, but I could not take a dot product between a 2-dimensional vector and a 3-dimensional vector. They have to be the same size. The dot product has these properties. They should sound familiar to you. It's commutative, which means the order doesn't matter. It's distributive, which is exactly what I'm showing you on the screen. It's associative, kind of like regular multiplication of scalars is commutative, distributive, and associative. So those are nice properties. It makes it easy to work with. If I multiply any vector times the 0 vector with a dot product, obviously the resulting vector is 0. So this isn't super clear, but I mean, I guess this equation is true whether this is a scalar or a vector. But like if I've got some 0 vector dot product with any other vector, that's still the 0 vector. Or sorry, no, that's not a 0 vector. Because why? Because the dot product is always a scalar. So that's 0. 0 times a plus 0 times b plus 0 times c. And then the last thing is going to be important. Think about this. If I were to take the dot product of a vector with itself, that's the same thing as if I were to take the norm of that vector and then square it. Okay, let me show you. I've got a vector ABC. If I wanted to take the norm of this vector, that would be the square root of a squared plus b squared plus c squared, right? And so now if I want to do the norm squared, that cancels out the square root. And it's a squared plus b squared plus c squared. What would the dot product be of u dot u be? A times a plus b times b plus c times c. So this is true. And we're going to need to use this later. Okay. Exercise 2 says, state and prove the law of cosines. So this is a throwback to geometry class, right? Hopefully everybody did this in high school. If I happen to have a triangle, like this lovely purple triangle, and And I want to say that these side lengths are going to be A, B, and C, and the opposite angles are going to be my nice Greek letters, alpha, beta, gamma. Then what I want to prove is this. It kind of looks like the Pythagorean theorem, but it's tweaked a little bit. It's tweaked because this triangle does not have to be a right triangle. The angle gamma and beta and alpha, for that matter, can be whatever I want them to be. And this is always true for every triangle. How I would prove this is I would start by drawing an altitude of the triangle, which is to say, pretend the side B is horizontally flat, and then what I've just drawn here, pretend that's completely a vertical line. And when I do that, I can connect this vertex to the other side in a way that creates two right angles. And the good news now is that I have sort of split up my big purple triangle into two smaller triangles. And these smaller triangles obviously are triangle ADE, and then this triangle over on the right has sides CD, and this is going to be a little bit important here. This is not the length B, but it's actually B minus E, because B is supposed to be the whole bottom of the triangle. Now, there's 3 ingredients in this recipe. First of all, the cosine of gamma is what ratio? Perfect. Cosine is the adjacent side over the hypotenuse, and in this case, cosine of gamma is going to be E over A. And that means E is the same thing as A cosine gamma. Okay, that's one ingredient in our little recipe. The second one is going to be what I get if I apply the Pythagorean theorem to the left triangle, which is to say E squared plus D squared equals A squared. And then the last ingredient here is what happens if I apply the Pythagorean theorem to the triangle on the right. I'm going to end up with D squared plus B minus E squared equals C squared. So over here, let's go ahead and expand the B minus E squared part. So it's going to look like D squared plus B squared plus E squared minus 2BE. And let me rearrange this equation so I can say D squared equals what? A squared minus E squared. Very good. So we are almost ready to cook. First, we combine these ingredients. What I want to do is I want to replace this D squared with A squared minus E squared, since those are equivalent. And if I replace this D squared with A squared minus E squared, what I'm going to get is A squared plus B squared minus 2BE equals C squared. Where did the e squareds go? They cancel out. So I got a negative e squared, and I got a positive e squared. So I got rid of them. And then who can tell me what's the last step? Yeah. Sorry, I spoiled it. I should have given you a little bit more time to think, but that's okay. That's what we were trying to find. That's the law of cosines. Okay, everyone's happy with that? Any questions? No? Okay, so we need the law of cosines because this is a very, very important fact of geometry right here. We are going to give a formula for finding the angle between two vectors, and the formula is based on the dot product. Okay. If I want to know, I've got two vectors u and v in space. I want to know what's the angle between them. Let's say the angle is theta. I can find this angle by taking the arc cosine of u dot product with v divided by the norm of u and divided by the norm of v, like it says there. So this is the third one on the screen is basically giving you an explicit formula for how do you calculate that angle if you're asked for that angle. A lot of times in textbooks, it appears in the second form, right? Like if you're picking up a calculus textbook off the shelf, most of the time it'll just say cosine of theta equals u dot v over norm of v. But you can easily see how you get from those, right? How to go from 1 to 2, you just divide both sides by norm u, norm v, and then obviously arc cosine is the inverse function of cosine. So these are all equivalent. Doesn't matter which one you want to memorize, but you do have to memorize one of these, right, for your next test. You need to be able to use this on a test from memory. And if you memorize one of these formulas, you should easily be able to tweak it, manipulate it, and get it to the form you need to use on the test. So one of these. Now, how can we prove this, right? This is a little bit strange, I hope. I hope it's a little bit strange that we can find the angle between vectors by taking their dot product. Let's talk about it. Here's my vector u. Here's my vector v. And this vector over here, where its tail is at the tip of v and its point is connecting to the point of the u vector, this vector would be the vector u minus v. And to me, I don't fully wrap my head around that immediately, but think about this. V plus u minus v is equal to what? U. And you also remember our picture of vector addition. Whenever we add vectors, it's basically the same thing as lining them up tip to tail, and then you see where it ends up. And so since this vector ends up in the same spot as u, it must be u minus v. So now we've got a triangle. And the great thing with triangles is that we can always apply the law of cosines. Even if it's not a right triangle, the law of cosines still works. And the law of cosines says something like a squared plus b squared minus 2ab cosine gamma equals c squared. Well, this time, what is a? Yeah, In fact, it's going to be the norm of u, because we're talking about side lengths. And not the vector itself, but we only want the norm of the vector because we want the side length of this triangle. What's b? Yep. And again, v is a vector, but what we really care about is the side length here. So we're going to use the norm of v minus 2 norm of u, norm of v, cosine of, we'll call it theta, because I wrote theta here in the corner. And theta is the angle that's opposite this side. And this side length in the law of cosines is the lowercase c. But in our case, that is going to be the norm of u minus v squared. Okay. So again, this is just so far making up a triangle made up of two vectors and their difference, and then also applying the law of cosines to it. For our next trick, we have to remember that if I take the dot product of a vector with itself, it's the same thing as that vector's norm squared. Do you remember I circled that on the previous page and I said, remember this one? Okay. So where I've got u squared, or sorry, the norm of u squared, I could write u dot u, and that's the same thing. Where I've got the norm of v squared, I could write v dot v. And then I've got 2 norm of u, norm of v, cosine theta, equals, and then this is going to be u minus v, dot product, u minus v. And because this dot product is distributive, that means I can expand this right side and write it as u dot u plus v dot v minus 2u dot v. And that's me applying the distributive property of the dot product on the right side of the equation. The left side of the equation is going to be the same for now. And I don't want to get carpal tunnel, so I'm just going to leave that like that. Trying to save myself a little bit of time. Okay, so once I'm here, I've got this left side of the equation, this right side of the equation. What do I do next in my proof? How do I simplify?
You can subtract u dot u and v dot v.
Great, Connor's right. Let me subtract u dot u and v dot v. And then I will have negative 2 norm of u norm of v cosine theta is equal to negative 2 u dot v. All right, and what do I do as my last step here to simplify this equation?
Divide by -2.
Divide both sides by negative 2. And that should look familiar. That's what we've been trying to prove. So this is the proof of the fancy formula for finding the angle between two vectors. If you know what the vectors are, you can take their dot product, divide by their norms, and then take the inverse cosine. And this is what we end up with. Okay? Questions? That's proof number 2 of 3 of this lecture. There's another one coming up, but we're Hopefully they're not too crazy, right? It's like 5 or 6 steps. Here's a question for you guys. If I have u dot v equals 0, what does that say about the angle between my vectors? If their dot product is 0.
If I remember right, it's perpendicular.
It's perpendicular, yeah. So again, if you see any question about angle between vectors, what you should be thinking is cosine theta is equal to u dot v over norm u norm v. And since this dot product is 0, the whole right side of this equation is 0. I'm basically saying cosine of theta equals 0. For what angles is cosine of theta equal to 0? It's for 90-degree angles, right? So this is why it's good to know your unit circle. But the answer to exercise number 4 is to say theta must be pi over 2 or 90 degrees between the vectors.
Can we not say 270, or is just the 70 to circle to 6?
If I'm asking you about the angle between two vectors, always choose the smaller angle, right? Like if this is my angle between the vectors, I want you to tell me this angle and not this angle all the way around, you know? Just choose the smaller one. So it should always be less than 90 degrees. Okay, so new definition, new vocabulary word. We're going to use the word orthogonal sometimes in this class. If you've taken a linear algebra class, you've probably seen the word orthogonal before. But if you've got two vectors in a two-dimensional xy plane, whenever they have a 90-degree angle between them, we say they are perpendicular vectors. But we could also just as accurately describe them as orthogonal vectors. Vectors that have a 90-degree angle between them are orthogonal to each other. And moreover, we normally use the word orthogonal when we want to generalize the word perpendicular to higher dimensions, like 3 dimensions, 4 dimensions, 5 dimensions, and so on. You could have vectors that you can even have more abstract interpretations of the word vector that are orthogonal to each other. We can talk about orthogonal functions, orthogonal polynomials in other classes, but not in this class. But it's basically just remember in your head, what does the word orthogonal mean? It basically means perpendicular, but it's applied to more situations. Okay. Our definition that we care about in Calculus 3 is that they are orthogonal if their dot product is 0. The angle between the vectors is 90 degrees, and so we say that they are orthogonal when the dot product is 0. This next one is, again, a question for the audience. If u dot v is equal to the norm of v times the norm of u, what does that say about the angle between those vectors? Yeah? Parallel. Yeah. They are pointing in the same direction. And again, this is an easy question to answer on your test, as long as you remember that this is true because you memorize it. Some variant of this formula. You think, okay, if u dot v is equal to norm of u, norm of v, then the left side of this equation is 1. And you think, for what values of theta is cosine theta equal to 1? It's 0 and pi. But we always choose the smallest angle, like Carter said a moment ago. We're going to choose the smallest angle, and this time the angle is 0. And so there is a 0-degree angle between these vectors, which means they are parallel vectors. The vectors point in the same direction. So you might have an exercise like this that says find the angle between those two vectors. Again, not hard as long as you have memorized this formula here. So we need some things. U dot V is what? Five. What is the norm of U? Square root of 11. What is the norm of V? Square root of 5. And so we can write cosine of theta is equal to 5 divided by the square root of 11 square root of 5. We can even say that the cosine of theta is like the square root of 5 over 11 if you want to. And then what you would do in your calculator is you actually type in the keys arc cosine of the square root of 5 over 11. And then boom, you've got an answer from your calculator at least. Now that I think about it, I don't even know if your calculator has an arc cosine button. I'm like 90% sure that it does. Daisy can tell us.
It does.
It does, cool.
Cosine everything.
But you know, the other thing too is that this is not calculator class. So if you just write this as your answer, that's also perfectly fine. I would give you full credit if you just write something like that instead of writing like a decimal expansion. If you just want to write the decimal expansion, then go ahead, you know, be my guest. I will also give you full credit for the decimal expansion. But obviously I know that you know what you're doing if you write that or the decimal. Okay, guess what formula we're going to need for exercise number 7? The same one. There's not a lot of variety today. Okay, so what am I given? I'm actually given the norm of both vectors. And if the angle between those vectors is 30 degrees, then what is cosine of theta? Yep. And that's what I'm trying to find, the dot product of U and V. So 5 times 6 is 30. 30 divided by 2 is 15. That's the dot product of those two vectors. Suppose U and V are distinct vectors. We can break U into two component vectors. Okay, so this is new. This is not the same formula. We're going to learn these words, or these terms. Sometimes I want the projection of U onto V, and so I use the letters P-R-O-J for projection. And the rejection of u from v is rej for rejection. In a two-dimensional sense, let's say this is the vector u, and this is the vector v. Projecting u onto v means I find a vector that's pointing in the same direction as v. But how do I determine the length of the projection of u onto v? I only take the component of u that's in the v direction. And the rest of it is what we call the rejection. We call this part the rejection of u from v. And the projection of u and the rejection of u are orthogonal to each other. And so it's important to note that this angle here is like a 90-degree angle between the projection and the rejection. And when I add the projection plus the rejection, I get the original vector u back. So when I line those up tip to tail, then I get u, my original green vector here. Make sense? So, exercise 8 on your homework says, given the vectors u and v and the two component vectors u1 and u2, please verify that u1 plus u2 is equal to u. Okay? And so you would just add these together. 3/2 plus -1/2 is 1. That checks out. Second entry, 3/2 plus 1/2 would be 4/2, which is 2, and that checks out. And then lastly, 0 plus 3 is 3, so that makes sense, right? First bullet point checks out. The next thing I need to verify is let's make sure that u1 is parallel to v. And what you remember from last time is that if it's parallel, then u1 is equal to some constant times v. What is that constant? Three halves. The u1 vector is equal to the v vector times the constant 3/2. And so that means yes, u1 is parallel to v. And then the last thing we got to check over here is u2 orthogonal to v? And if I want to check that something is orthogonal, that means I have to take the dot product. So -1/2 times 1 plus 1/2 times 1 plus 3 times 0 equals 0. And so yes, that means they're orthogonal. Remember, the definition of orthogonal is that their dot product is 0. And so that means that u1 is going to be the projection of u onto v, and u2 is going to be the rejection of u from v. So in that example, I gave you the projection, I gave you the rejection, I asked you to verify that everything was true. But if you don't actually know what they are to begin with, this is how you're going to find them. And this is our third proof of the day, or this is the last one. We have this formula for how I can find the projection of u onto v. And this is u dot v divided by v dot v times v. Remember that dot products are scalars, right? So I've got a scalar divided by another scalar, that makes a scalar. Everything inside the parentheses is just a scalar. So I've just multiplied the vector v, and that means the resulting vector is going to be pointed in the same direction as v, which is good. That's what we want. And it's going to basically be the vector v itself, just scaled up or down by some number. Now, you can see the formula, and you probably recognize this is one of those things that you'll have to memorize. And then again, let me show you what the proof is. How do I know that the projection of u onto v is equal to this formula? And what we would like to do is have the projection of u onto v be, let me draw a picture. I'll draw the same picture I drew before. We want this to be some kind of constant that scales a vector in the direction of v. Do you remember what the little hat means from last time? Yes, the little hat indicates that this is a unit vector. And if I put a v hat, that tells me it's a normalized version of v. And specifically, I'm talking about v divided by the norm of v. Because that makes the norm of v hat equal to 1. In other words, I don't have to worry about multiplying by v hat and changing the length of this vector. The length is going to stay the same because I'm multiplying by 1. But what v hat does tell me is it gives me a particular direction. Multiplying by v hat will give me a direction to my vector, but it won't change the magnitude. And so I know it's going to be some scaled up or scaled down version of this particular direction. And what's left for us to figure out is how much does that need to be scaled up or scaled down? In other words, what we're trying to figure out is how long does the projection of u onto v need to be? But look, I've got a right triangle. That's pretty nice, geometry-wise. So I can write that the projection of u onto v, norm squared, plus the rejection of u from v, norm squared, is equal to the norm of u squared. That's the Pythagorean theorem for my right triangle right here. And moreover, if I take a look at this angle right here, and I call this angle theta, what is cosine of theta? It's the angle between the vectors u and v. And so that means it would be u dot v over norm u, norm v. And in terms of this right triangle, the cosine of theta would also be adjacent over hypotenuse. Cosine is the ratio of adjacent to hypotenuse. And so this is also going to be the ratio of the projection of u onto v, norm, over the hypotenuse, which is the norm of u. And so this constant k that I'm looking for is really just supposed to be what's going to be the magnitude of this vector when we're done? And I bet you can already put this together by yourself if you really try. What I'm going to do is I'm going to take this equation here now, multiply both sides of this equation by the norm of u to get it out of the denominator. And then I'm going to use that here so that I can write u dot v over v norm. And then where there's a v hat, I'm going to replace that with v divided by v norm. Now you get to slide over the v norm into the denominator here. And this is what we've been trying to prove. If there's one thing that I failed to say out loud, it's that the norm of v times the norm of v is the same thing as v dot v. That was a fact from super early on this lecture. In fact, I haven't even yet used that Pythagorean theorem identity. Sometimes I don't really know where a proof is going, and I don't remember this from the last time I taught the class. So I just start writing facts down. And that's a perfectly good proof writing strategy, right? If you are trying to write a proof and you don't know exactly where you're going, just start writing down everything you know about the problem. Eventually, something's going to stick. This time, the Pythagorean theorem ended up not being helpful, but maybe next time it would be helpful. So just got to give it everything you've got. Okay, any questions? Does that all make perfect sense to you guys? Kind of? Is there one specific spot where you're like, that, I don't understand that step? Or just kind of in general?
Just in general. I follow it, but it'd be a little bit hard to get on.
To reproduce it, yeah. I know what you mean. Okay. There is a lot packed into these first sections. So we started at 12:15, right? Okay, so we still have until 1:30. Oh, we might still make it through. I'm just looking at my page 12 of 23 at the top, and I'm getting a little bit nervous, but we can do it. Okay, we know how to find the projection of u onto v. There was a formula on the previous page. But how would you find the rejection of u from v? And this is actually where that Pythagorean theorem could come into play, right? If I already know this one, oh shoot, I don't even need the norm part. I don't even think I need the Pythagorean theorem. Hold on. Let's go back to my picture. I'm making this more complicated than it has to be. If I already know what u is, and I already know what the projection of u is, how do I find the rejection of u from v?
Would it be like projection of u on v plus the rejection equals u?
Yes. Yeah, exactly. This is just a picture of what addition looks like for vectors. If I want to add this one plus this one, then I get this one. The projection plus the rejection is u. So if I already know what the projection is, I just do u minus its projection, and that will give me the rejection. Thank you. Very good. I was about to make that harder than it needed to be, but u minus its projection is its rejection. So in exercise 11, it says, find the two components of A that are parallel to and orthogonal to B. What does it mean if A is parallel to B? or what if I say there's a component of A that is parallel to B? That means it's the projection. And if there's another component of A that's orthogonal to B, that would be the rejection. Perfect. And then the projection formula is A dot B over B dot B times B. A dot B is 4 times 1 plus negative 3 times 0 plus 1 times 1. B dot B is 1 times 1 plus 0 times 0 plus 1 times 1. And then if I multiply 5 over 2 times B, I get the vector 5 halves, 0, 5 halves. And then to get the rejection, I start off with my A vector. I subtract the projection. And then I get that, right? Easy. If I say something's easy, I don't want to make you feel bad if it's like really hard for you. If I say something's easy, know that I just mean it's easy relative to the other stuff that we'll be doing this semester. That didn't sound right. I'm really trying hard not to be discouraging. I'm trying.
Put the shovel down.
Yeah, okay. This might be, this is our first calculus problem, you guys. We've been doing geometry this whole time, and now we finally have calculus. You might be familiar with how these curves look in the xy plane. What if I want to find the angle between these two curves at their points of intersection? And I'm 90% sure that if I give you this as a test question, I'm going to give you a picture to look at. And it'll be a picture of the curves. It won't be a picture of ducks or anything. But this is the cube root. This is x cubed. So you know what we're talking about. And points of intersection. We know from symmetry that whatever the angle is here, it's going to be the same angle here. And then here might be a different angle. I don't know. But how do we do this? And it's kind of a process. This is kind of a long question. Number one, if you haven't already done so, you need to find out where this intersection is going to happen, right? These are relatively simple functions. We know where they intersect, but maybe if you didn't know where the curves were going to intersect, then you should like set them equal to each other, right? Like if I didn't know this off the top of my head, I'd say x cubed equals x to the power 1 over 3, and then you could work out the equation and find out where the zeros are, or where they're equal. You know what I mean. Solve the equation, and you'll find the points of intersection. This time they're at -1, 0, and +1. Next, for a given point, like let's talk about point A first. What I need to do is I need to rephrase or re-describe, I need to describe both curves as parametric curves. Did you do this in Calculus 2? Do you remember parametric curves from Calculus 2? You sure? Okay. Okay, one little aside here is that a parametric curve starts with some parameter. And this is just a scalar. My little lowercase t is a parameter. It's a variable that could be any real number. And then I'm going to get these coordinates along my curve that are given by x coordinate as a function of t and my y coordinate as a function of t. Okay? Let me demonstrate. If I say cosine of t comma sine of t, and I let this go from 0 to 2 pi, I get a circle. And so when t is equal to 0, my x-coordinate is 1 and my y-coordinate is 0. And then as t increases from 0 to 2 pi, it traces out all of the points along this red circle. This is what we call a parametric curve because I've defined it using a parameter t. And it's kind of a fun thing to do since you've never done it. On Desmos, see what other shapes you can make with parametric curves. Just by plugging in different closed functions and, ooh, that's a nice one. Messing with it. But what makes this a parametric curve is, again, I'm allowing t to have a continuous interval of real values, and then I calculate corresponding x and y values for a given value of t. And that means my curve isn't just a function as y as a function of x anymore, but y and x are both a function of t. Okay. Another thing you can do in Desmos is this. Hold on. I want it to be a little bit less crazy. Like that's fine. You can kind of see how this is traced out whenever this parameter starts at 0 and then goes up. You can see the little dot that races around. And so for a given value of t, you can see what point along the curve it corresponds to. So when t is equal to 2, we're talking about that point right there. Okay, back to this. No, back to this. What I need to do is I need to rephrase y equals x cubed as a parametric curve. And so for me, that means let's make x the function t squared, and y is going to be the function t. I said t squared, I meant t cubed. Oh, no. Backwards. Backwards, you guys. You gotta catch me when I make these mistakes. Y has to be t cubed, because if x is t and y is t cubed, then y is x cubed, and that's what I want. Now hopefully that makes more sense. But now this can be my parametric curve. And another way to check your work, obviously, is you could go back here and you can type in y equals x cubed. And that's the line you should have. And then you can type in t comma t cube. And just make sure that you're getting the same curve, whether you define it as a parametric curve or a explicit curve. Okay. The other one, which is the cube root, we could define like, and I should have stuck to a better color convention. I should have stuck to orange, but I didn't. The other one, which is the cube root, I could, for one way to do this, keep x as the parameter t, and then y can be the cube root of t. There's another way I could do it. I could actually make x t cube and y t if I want to, because parametric. But we won't be that fancy today. So I've got my orange curve and my green curve, and at this point what I need to do is take the derivative with respect to t. And so taking the derivative with respect to t is going to give me 1 3t squared. Taking this derivative with respect to t is going to give me 1 and 1/3 t to the power negative 2/3. Okay, so now again, let's think about this point A. This occurs at the point where x is equal to 1, and since x is equal to t in my parameterization, then that means this is the point where t is equal to 1. And so when I look at my derivative vector on this orange curve, when t is equal to 1, then at t equals 1, the orange curve has the derivative vector 1, 1. No. 1, 3. Cool. And then what about the green one? What about my green? If t is equal to 1, then this derivative vector is 1 and 1/3. So what these derivative vectors are doing is they are saying, if you zoom in really close to these parametric curves, then what direction are they moving when t increases a little bit? From like t equals 1 to t equals 1.001, what direction are we moving in? And when we ask a question like, what's the angle between curves? What we're kind of asking is, when you zoom in really, really, really close to the curves, and the curves are so close and so zoomed in that they basically look like lines, then what is the angle between these vectors? And again, those vectors are the derivative vectors. So now you already know how to take the angle between vectors. It's that nice formula that cosine of theta equals u dot v over norm u norm v. And so take their dot product. You got 1 plus 1 is 2. The norm of this is going to be square root of 10. The norm of this is, I don't know. That's like 1/9 plus 1, so 10 over 9. The square root of 10 over 9. And then square root 10 times square root 10 is just 10. The square root of 9 is 3. So cosine of theta is 3/5. Now I don't know what the arc cosine of 3/5 is because it's not a nice number. But that would be the angle that we're talking about between those two curves where they intersect at x equals 1. The other thing we could do is we could do the problem where x is equal to 0. I can already tell you that that's going to be a 90-degree angle between those curves there when x is equal to 0. But I don't think we have time to actually work that problem because it's already getting close to ringing the bell. So you'll have to trust me on that one. A child pulls a wagon with a force of 65 pounds along a handle. It makes a 45-degree angle with the ground. So here is the child's spherical wagon, and here is the spherical child. That's always the joke from physics class, right? Is everything is a sphere. Everything's a point mass. Sorry. This is a 45-degree angle. And we are pulling with a force of 65 pounds. And we're going to do this for 40 feet. So this is your formula that you need to know from physics class. Work is equal to force times distance. And so you might think, okay, force is 65 pounds, distance is 40 feet. 65 times 40 is my force. But I actually only care about the force in the direction of the distance. So what I need to do is I need to find this component of the force. There's another component of the force that is orthogonal to the direction we're pulling the wagon. And then there's the horizontal part that is actually in the same direction. And this is going to be easier than having to do the whole projection formula because this is a 45, 45, 90 right triangle. And so I know that this is actually just square root 2 over 2 times 65. And so this time the work is easier. And this would be in units of pound-foot. Good old-fashioned American units. Suppose u, v, and w are non-zero vectors. You guys can tell me real quick. Why is this expression not defined?
Because the dot product makes it a scalar.
Perfect.
And you can't add it to it.
Yes. I can only add scalars together or vectors of the same size together. But Alex is right. A vector plus a scalar doesn't make sense. I can't add a vector to a scalar. What can be said about the vectors u and v when the projection of u onto v is equal to u? No. I would only use the word collinear when we're talking about points in space, but you're on the right track. What's a better word for that when we talk about vectors?
Are they just like the same vector? Like equal distance, equal direction?
No, not exactly the same.
Parallel.
Parallel. Yeah, I think y'all had kind of the right ideas. They are in the same direction, right? Maybe that's u and this is v. but what's important is that they are parallel. And that's why I said, collinear is kind of the right idea. It's just not exactly the right vocabulary for vectors. But two vectors that point in the same direction are parallel. And in this case, if the angle between them is 0, then that means the projection of u onto v is the vector u. There's no component of u that isn't in the same direction as v. What can be said about the vectors u and v when the projection of u onto the vector v norm is equal to the norm of the projection of v onto the vector u? This is a real good question.
Do they have the same norm?
Yeah. Yeah, this would just mean that they have the same norm. The answer to the question is that the norm of u must be equal to the norm of v for this to happen. And, we can go back to the projection formula and think about it for a minute, and then we'll call it a day. But the projection formula says I've got u dot v over v dot v times v, right? And this is supposed to be just the norm, right? And so we do this. And then if I flip it around and take the norm of the projection of v onto u, this would be v dot u over u dot u times norm of u. Now, v dot v is the norm of v squared. U dot u is the norm of u squared. And so this norm of v cancels with one of those norm of v's. This norm of u cancels with one of those norm of u's. The dot product is commutative, so these actually have the same numerator. And the only way that 1 divided by norm of v is equal to 1 divided by norm of u is if norm of u is equal to norm of v. And so it has nothing to do with the angle between them, what direction they're pointing, and it just turns out this is always true if their norms are the same. All right, so I guess that's all we have time for. Y'all have a good day.